Okay, so we're going to see what conclusions we made about the dot product here. So what about what did you find if vectors A and B have the same direction? If they have the same direction, was that something that you discovered? Yeah. Okay, so she's saying it's the product of the magnitudes. Did you find that? So you get okay, the product of the magnitudes. All right, so what other, anyone make another discovery, observation about this dot product? Yeah?
When they have opposite directions,
yeah?
It's a negative product of the magnitudes.
All right, so he wants opposite directions. That's my number 4. Agree with that? All right. Yes, sir. Okay. Yeah.
When the product results in a 0, the vectors form a right angle.
Okay, right-angled vectors, and you get 0 for the dot product. Okay. Yes, sir.
When the dot product is negative, you have an obtuse angle.
Okay. So let's do it the other way, right? Because we're starting with the angles, and then we get the dot product. So if we do it the other way, we'd say that if the angles form no, what he said was perfect. It's just that we're going to start with vectors, and then we're going to get the dot product. So we're going to start with these vectors, and we're going to look at them, and we're going to say what?
So the angle's obtuse, which means it's going to have a negative.
Right. So we're gonna take these two, and we say, okay, there's an obtuse angle. Okay. Let's see here. There we go. All right. This one. Or we could say it's obtuse, right? So they're obtuse, or we could say it this way. A has a component in the opposite direction of B. Would that be another way to say they're obtuse? If you took the component, there's a component of A that points exactly in the opposite direction of B. Do you see how that says the same thing as them being obtuse? And then, yeah, you get a negative dot product. Tom, are you going to do the last one?
The vectors are multiplied by the components in the same direction. So if like vector A, I'll use like the third example is 3, 4. I don't want to describe it, but the triangle has 3 in the x direction, so you multiply the 3 times the 5.
Okay, all right, so you're kind of getting at you're kind of getting at where we want to kind of, our grand conclusion in the end. So what other situation have we not covered yet? What other situation? Yeah, you're on the right track. Yeah.
If the vectors form an acute angle, then it is positive.
The dot product's positive, right? So in that case, you could say that what? That A has if they have an acute angle, tail to tail, then you could say one has a component in the same direction as the other, instead of the opposite direction, like obtuse, right? So looking at all these conclusions here, smaller. numerically, so when we talk about the numerical value of it, it seems like it's related to what? The numerical value is related to what? In all these cases. But the number doesn't relate to the angle so much, right? The number that you get, the dot product, is related to, yeah. Okay, don't just say what you learned last semester. What you about to just say. No, I just want to know what the number relates to. Just the number of the dot product seems to relate to what? Because this is the thing that people forget. What's that? Product of the magnitudes, right? The product of the magnitudes, okay? So, if they're in the same direction, you get the product of the magnitudes. If they're opposite directions, you get negative of the product of the magnitudes. And then as the angle changes, what happens to that?
It gets lower or
Yeah, so it's like we've got our product of our magnitudes, and then what? It starts decreasing. It's less than the product of the magnitudes as they're acute until we get to right angle, and the dot product is 0, and then we keep going, and now what happens? Yeah, it decreases negatively. It gets bigger negative until we get the product negatively. Yeah.
For the obtuse angle, wouldn't the product be greater than or not less than?
Negative, but less negative than. You're right. You're absolutely right. The way I phrased it, though, you're right. It's going to be greater than the least negative number, but I wrote less negative. Yeah. So we're both right. We're both right. Okay, so then how can we kind of put that all together? So it's essentially the product of the magnitudes, but it's affected by the angle. So, all right, Griffin, here's your thoughts.
It's the product of the magnitudes times cosine theta.
Okay. All right, so that's how we're going to get it, but what about the meaning, right? So yeah, that's right.
The same way.
Yeah, sure.
So if you look at it the way I figured it out, is that when you have them in the exact same direction, your angle will be 0.
Okay.
You have 1, like cosine of 0 is 1, so you have that's going to be your mark, so it's just going to be the magnitude.
Okay.
And then when you're at 90, the cosine of theta of 90 would be 0, so you have that 0.
Okay.
And then as you go back through, you get to the cosine of 180 or pi, where they're exact opposite directions.
Mm-hmm.
You get a negative 1. So that kind of goes for the whole span of going closer to 0, and then you go all the way back to that same thing, but in the opposite direction.
Okay. Yep, that's right. So can we be a little more, so can we come up with something that's more kind of idea oriented? What's the idea of it that mathematically is backed up by cosine, right? So what's the idea of this?
The dot product kind of goes up and then down.
Okay. But so it's the product of the magnitudes, but
Is it the third side?
no, could be the third side. So we get the product of the magnitude when what? When they're in the
Same direction.
same direction. We get 0 when they're orthogonal. So it's the product of the magnitudes, but okay. Oh, Griffin, you had your chance. Sorry. Somebody else. So it's the product of the magnitudes as that's not a smartphone, is it? Okay. It's a product of the magnitudes what? As much as what? What about the direction? Same direction, right? It's like as much as they're in the same direction, you get the product of the magnitudes. When they're not in any in the same direction, orthogonal perpendicular means they have nothing in common. It's not a smartphone in your lap, is it? It's not a smartphone in your lap, is it? It's not a smartphone in your lap, is it? It's not a smartphone in your lap, is it? That's not a smartphone in your lap, is it? Okay. Cell phone, yes, right. Okay, so when two vectors are orthogonal, small classroom guys, don't get caught. All right, so when two vectors are orthogonal, there's nothing in common about their direction, right? They're in totally different directions. There's no component of one in the direction of the other. That's why you get dot product of 0. So, and then in between, you get what? Part of, and that's what Griffin was talking about with cosine. So here's our big conclusion about the value of the dot product is what? The product of the vector's magnitudes as much as they are in the same direction. As much as they are in the same direction is the product of the vector's magnitudes. And this is going to be a really important. When we get to the end of the course and it gets really, really hard, this idea is going to be really important. All right, so let's look at an example here. Or let's look at work. So work is defined as the total amount of force applied over a distance. Okay, so that's our basic definition. All right, so we can investigate the amount of work to move an object. Work is a scalar, all right? Work does not have direction associated with it. It's just an amount. Okay? But we can figure that out by observing force vectors and the displacement, those are both vectors, right? Forces and displacement are both vectors, and so then those together somehow are going to give us this quantity of work. So here's an example of work. So a girl pulls a wagon with a force of 56 newtons, an angle of 39 degrees above the horizontal for a distance of 8.1 meters. What's the work applied to the wagon by the girl? So we can use vectors to kind of model the situation. So there's a force vector, right? So the force vector is this 56 newtons. She's pulling, right? And then the distance of 8.1 is really a displacement because we know the direction that that's in. That's horizontally, right? So we do a displacement vector like that, and its magnitude is 8.1. So I'm showing the magnitudes numerically, and then I'm showing these vectors, okay, as arrows. So what's the work? So we want to write the vectors f and d. Okay, let's see. Tell me your name back here with the Starbucks. Yeah, what's your name? Sochi. Can you tell me, I'll give you your choice. Can you give me the component form of either one of those vectors, f or d? No? Okay. Tell me your name right here. Yeah. Yes. David, can you tell me the component form of one of these vectors? Okay. But I want it as a vector, right? So that's just one of the components, right? So vector, R2 vector would have two components. Yeah. They're sine 39 times 56. Right. Yeah. So that's 56 cosine 39, 56 sine 39 would be describing that force vector, right? Force as a vector. What about the displacement vector? What would that be? No.
Wouldn't that not just be 8.10?
He wants 8.10. You got nods. You got lots of nods. Okay. So yeah, so F is 56 cosine 39, 56 sine 39. D is 8.10. So that's, hopefully most of us got that. That's important to be able to do that. So which component of F contributes to the work done? Which component actually contributes to the work done? The horizontal, right? The horizontal. The vertical, what? It's pulling up on the wagon, has nothing to do with the horizontal work, right? So it's pulling up, gravity's pulling back down, those balance out. So then all that's contributing to the work is the horizontal component. All right, so then calculate the work. Work is force times distance, right? So what would it be? If work is force times distance and we only need the horizontal component of the force, then the work would be what? So the force is 56 cosine 39, the distance is 8.1, right? So it'd be the force times distance, 56 cosine 39 times 8.1. Okay, so what? Notice that work is the product of the magnitude of the force and the distance, but only as much as they're in the same direction. You see that? So it's only how much force is in the direction of the distance that you're going. So that should be some light bulbs. Some light bulbs should be going off. What is that about? That's dot product, right? That's dot product. Okay, so that's the dot product. So notice that 56 was the magnitude of F, right? And then we had the cosine of the angle between them. So the angle between the vectors when they're tail to tail, right? The angle between when they're tail to tail, call it theta. So this is an alternate way to calculate the dot product. So in your homework, you did it by multiplying the like components and adding, right? But really more in line with the meaning is if you're taking the product of the magnitudes in as much as they're in the same direction, well, that's just the product of the magnitudes times, like Griffin was talking about, cosine theta. So if we did it the other way, right, we'd be doing it this way, like you did for your homework. You take the F vector dot the D vector, and you notice you're going to get the exact same thing. You're going to get 56 cosine 39 times 8.1 and then plus 0, because you're going to multiply the y components and get 0. All right, so this is super huge, important point. Does it make sense? So the moral of the story is there are two ways to compute the dot product. There are two ways. This way captures the meaning, right? Captures the whole purpose of the worksheet was to say, look, what is this dot product all about? Well, it's about the product of the magnitudes as much as the vectors are in the same direction. So that captures the meaning of it, and that's one way to calculate product of the magnitudes times the cosine of the angle between them. And then the other way will give you the same number, all right? So if you multiply like components and add up all those results, you get the same value. You'll get the product of the magnitudes and as much as they're in the same direction. So when you're doing problems and it involves dot product, remember there's two ways to compute it. So use whatever's the most efficient in the case, in the situation. And then this also allows us to solve for the angle. So notice if you didn't know the angle, right, but if you knew the two vectors, do you see how you could solve for the angle using this, using both sides, right? You could, if you knew the vectors, you could easily do this side. You can find their components, find their magnitudes, and all that would be left is cosine theta. You could solve for the angle between. So dot product is a way to solve for the angle between two vectors if you know the two vectors. And you're using the two different ways to compute dot product to do that, and then you isolate. So it's going to be inverse cosine of dot product divided by product of the magnitudes. Okay, any questions on that? All right, so here's an example. We've got a box back here. I'm going to draw the box. do it. So there's this like box back here. Sitting on the plane. How much work is done to push the box from -2, 1, 0 up the ramp to the point key shown if the force applied is 8, -15, 0. So we're going to come along with some force here like this. What kind of force is that? 8, -15, 0? How could you characterize that force? It's a force vector, but what's special about that force vector? What kind of force is it? Horizontal force. You see that's a horizontal force because there's no z component. So that's totally pushing horizontally on that box. So imagine you have a frictionless plane, and if you push on that, it'll just slide up, right? And so by keeping this constant force on the box, it's going to slide up to that point. So I want you to find the work to move it from -2, 1, 0 to -3, -6, 2. So I'll just give you a hint. There's a really, really hard way to do it, and there's a really, really easy way to do it. Which are you going to pick? Okay, and I'll take it, as you work on it, I'll take attendance. What time are we out of here? 12:40, right? Okay. All right, so let's talk about projections. Projections. So there's something called a scalar projection of one vector onto another, and there's something called a vector projection of one vector onto another. And so we're going to talk about, so you could do A, you can project A onto B, or you can project B onto A. So for our purposes, we'll just do B onto A. Okay, so we're going to talk about projecting B onto A. And what would it mean? What's the scalar projection of B onto A? Well, so it would be if you took what? As much of B that is in the direction of A, and just all you cared about was the length of that, right? The magnitude, a scalar. So, what would that be? What is that length? Just in simplest terms, what is that length? Yeah.
I was going to ask what the answer was to the last slide, but...
Oh, what'd you guys get? Yeah, definitely. What'd you guys get for an answer?
97.
97. You get it'd be foot pounds, 97 foot pounds. So work is force times distance, so that's the units. Sorry, yes, thank you very much. You should have got, it sounds like most of you got 97 foot pounds. Okay, so how would you just very simply calculate this length, just from your pre-calculus knowledge? Go for it.
B cosine theta.
Okay, what about B? Yeah, what about B?
The magnitude B.
Right, so B is the vector, so the magnitude of B times cosine theta, right? So the magnitude of B times cosine theta would be what this equals, right? But remember what is A dot B? So what is A dot B? Magnitude of their magnitude, product of their magnitudes, in as much as they're in the same direction. So, do you see another way that we could write this? So it's another way that we could write magnitude of B cosine theta. You see it's right there. So how could we rewrite, how could we get that value a different way? Yeah, so if you just solve for that expression, it would be A dot B over the magnitude of A. So that is what? That's the amount of B in the direction of A. The magnitude of the vector B is in as much as in the direction of A. So it's this very closely related to the dot product because it's right along with that idea that we talked about. Okay, so then what's the vector projection? Well, the vector projection then is, what's that vector, right? Now, not just what's the scalar, but what's that vector? So we have its magnitude already. And so we want the vector that has magnitude of that, and what direction do we want it to be in? So it has that magnitude, and we want it to be in the direction of A, right? And we've done that before, right? So how do you find a vector that has a certain magnitude and in the direction of another vector? Remember, this is really important that you know how to do this. What do you do first? Yeah, you're going to take A and make it into a unit vector, and so then we know it has magnitude 1, and then do what? Yeah, so we're going to take the unit vector in the direction of A, which is just divide by its magnitude. That should be familiar. So that scales it to a length of 1, right? That's the unit vector. And now we want to force it to be scaled to what we want, which is that. So now scale it by the amount of the scalar projection. So then we can simplify that as, so this can just come in and join here with the scalar, right? So we can just do magnitude of A squared times the vector A. So we get A dot B over the magnitude of A squared all times, just A. And so that's the vector projection, or that, is it orange on the screen? Barely. It's orange on my screen. So that would be that orange vector, the vector projection of B onto A. Does it make sense? Does it make sense? It's all stuff we've done before, but now we're just introducing this new definition. So let's just summarize here and then get the notation for it. So here's the scalar projection. We use this notation. Comp for component. So it's the component of B on A. So the subscript is the A, the one you're doing it onto. Okay, and then here's the projection of B onto A. So the formulas are the same two ones we came up with, but this is the notation now for scalar projection, vector projection. And likewise, we could start over and we could do the scalar and vector projections of A onto B. And that would be doing something like, I don't know, is that longer or shorter than B? If you projected that down there. Yeah, that's not great. Let's pretend it's longer. Because that's not, right? It's not usually going to happen that way. So you'd have to extend. So to get the projection of A onto B, you need to extend the line of B. So sometimes that happens where you have to extend the line of B, a line in the direction of vector B in order to find where that other vector hits on its projection. So if this is the right angle like this. So for instance, if A was like this, if they were obtuse, A was like this, you'd have to extend this line in the direction of B like this, and then your projection would be like that. Okay. So you flip everything around, and so then you'd have the magnitude would be this much, and that vector from there to there would be the vector projection of A onto B. So you can always start by whatever you're projecting onto, just make that into a line. And then you're going to just take the perpendicular component or the parallel component of your one vector onto that line. Okay, so be on the lookout for the problem. We're not going to do, for time's sake, we don't have time to do examples, but be on the lookout in your web work for problems that are going to use this to make it easy, and if not, you might go down a very hard, windy road. So be on the lookout for situations where having this scalar projection, either scalar or vector, is going to be really helpful in solving the problem. So you just kind of try to remember that you have this tool. It can really help you solve some of those problems. So that's just heads up. Okay. So that leads us to, let's talk about vectors. So we've talked about two kinds of multiplication with vectors. First kind was scalar multiplication, and that multiplied a what by a what, resulting in a what? Should know this. And then we had,
Scalar by a vector.
what's that?
Scalar by a vector.
It multiplies a scalar by a vector and results in what kind of thing? Another vector, and what's the meaning of it? What's the meaning of that resulting vector that you get? Okay, yep. So it's like a scaled version of the original vector. It's a scaled version of the original vector. It's going to maintain the direction. Or if that scalar is negative, it's going to be in the opposite direction. So it's going to be parallel. We'll know for sure that that resulting vector is going to be parallel to the original vector, and it's going to be the scaled version according to what the value of your scalar is. Okay, dot product. This is a way of multiplying two vectors together, and we get a number. And we talked about what that number means. So see if, without looking at your notes, see if you can personally write down a meaning for a dot product. Just everyone try it by yourself, and then once you got it written down, then have a little 30-second chat. So think everyone by yourself, so you can remember that meaning of dot product. Okay, so now you've written something down, so confer with the person next to you. Make sure you come to a consensus. What does the dot product mean? Okay, somebody new, who wants to tell me what they learned today? What's the meaning of the dot product? Tell me again. What's your name again? Rebecca. What would you say the meaning of the dot product was?
So the magnitude of two vectors multiplied
Right.
in relationship with their direction.
Okay. How about someone else? Is it Paul?
Yes.
What did you say, Paul?
It's the product of the magnitudes of the two vectors as much as they are similar in direction.
Right. So yeah. Right. So with the product, as much as they're in the same direction. If they're not at all have the same direction, then we get. So that's why when two vectors are what we call orthogonal. I didn't mention that, right? So perpendicular vectors we call orthogonal. That's the characteristic they have. They're orthogonal. Their dot product is 0 because they share nothing about the same direction, right? Okay, so then there's a third type of multiplication, and that's called the cross product. And the cross product, it multiplies a vector by another vector and results in a third vector. And that's what the sheet I just handed out to you is, extras. More extras? Everyone get one? Everyone get one? All right, so cross product is the third type of product multiplication in vectors. Multiplies one vector by another vector and results in a third vector. Okay? So this is going to be the same kind of deal. We're going to look at these 7 kind of baseline cases and then compare it to these. So, but it's a little bit different, because here I'm going to tell you, I'm going to tell you what the answers are. So you're going to try to sketch all 3 vectors in R3. Remember, your x-axis is coming out at us, y-axis positive to the right, z positive is up. So you're going to sketch all 3 for those 7 cases, and then for these down here, you do this over the weekend. We can start the 7 now up at the top. But for these down here, you're going to draw the initial 2 vectors that you're taking the cross product of, and then based on the 7 above, you're going to try to guess what you think the result is. Okay, so if you've ever done cross product before, just don't use, like, if you've learned the algorithm, or if you learned something about it in the past, just pretend you never have, okay, for this exercise. Because we really want to kind of figure out what cross product is. So you'll be kind of making an educated guess as to what you think that the resulting vector is in the bottom part of the sheet. So let's work on just drawing the first 7 there and see how that goes, so you can compare with the people next to you, and I can help just so we're making sure we're drawing correctly. So you're drawing 3 vectors in each. And if somehow you can make the resultant cross product vector stand out, maybe make it bolder or use a different arrow tip or something, so you know which 2 are the original and which one is the cross product, that could help. All right, so just as an example, I did the second one there. -2, 1, 0, -3, 0, 0, and 0, 0, 3. Is that what you got for in terms of the sketch? Okay, so you're just gonna, just note that what's the magnitude of this? 3. What direction is it pointing? Positive z direction. Where are these 2 vectors? So we can say these vectors are what? Both in xy plane. So this is the kind of things you're trying to notice. Both those vectors in the xy plane. The resultant vector is positive z-axis. It has a magnitude of 3. And so you're going to kind of look at these first 7 examples. I tried to give some real baseline examples and see what kind of patterns you can pick up on, generalizations you can make, and then use those patterns and generalizations to try to predict what the rest of them will be. Okay? So I won't see you till Wednesday. So that will be part of your written homework. And I'll post, this afternoon, I'll post the written homework that you worked on in recitation. And that's also due Wednesday in lecture. Yeah, and there'll be web work due Wednesday. The next web work will be due Wednesday, written homework due Wednesday, and this is part of the written. Oh, so this is what I'm going to do on Blackboard. In the homework section, I'm going to make a post for every day of the week, and it'll have everything. It'll have web work and written and or. Okay, so you can check Blackboard all the time for the next class what's due. Okay, so that's different than what I said before.